Okay, so our next speaker is Florian, presenting Incremental LM Cut.
Thank you. Okay, so this is also joint work with Malte Helmert. Did you turn it off again? Okay. So I will briefly go over the theory. Jörg already gave a great introduction yesterday, so I can probably be very fast here. So I'm talking about in the framework of strips planning. And the example task I want to use is a task where you have a set of rooms and some doors between the rooms, and some of them are closed and some of them are open. You have to pick up these diamonds here. And I only want to talk about openings and opening doors. It just makes it easier. So I can probably skip explaining what heuristic search is. Does anyone want to know? No? Okay. So Jörg already explained what a landmark is. So just to remind you, it's a set of operators, and every plan needs to contain at least one of them. So I'm talking about disjunctive action landmarks here, not fact landmarks. So since we need to use one of them, we have to pay at least the cost for the cheapest operator. That's why we say the cost of a landmark is the cost of the cheapest operator contained in it. And there are a lot of different choices for this landmark. In this state, for example, we have to open door A sometime to get to treasure to the diamond A1. So Jörg already mentioned the LM cut heuristic, and I don't want to give much more detail. Just one more thing is that to actually compute the cuts, the Hmax cost of each state is calculated, and this works under the assumption that we only have to pay the cost for the most expensive subgoal or the most expensive precondition of an operator. So if the Hmax cost is infinite, that means the task is unsolvable and we can stop the whole computation. If the Hmax cost is 0, then that means the LM cut algorithm will not discover a new landmark and we can stop for this iteration. And in all other cases, we can use the Hmax values for the variables to find a new landmark. If we discovered the landmark, we will reduce the cost of each operators in this landmark by the cost of the landmark. And this way, this introduces a cost partitioning that makes sure that the sum of all landmarks that are discovered this way is actually an admissible heuristic. And we just repeat this step until the Hmax cost reaches 0. So what I want to talk about is the incremental computation of this heuristic, and this is based on the idea that if we apply an operator and we reach a new state, we don't have to recompute every landmark. So in this case, assume that these are the landmarks that are discovered by the LM cut algorithm. And now consider what happens if we open the door B. So the first landmark here, this one, actually says that in every plan we need to open door A. But if we open door B, we are in a different state, but we still haven't opened door A, so this remains a landmark. And actually, the same argument goes for the last landmark too, but for the second one, we cannot use the same argument because we just applied operator OB. But with some reasoning, we can probably find that we still have to open door C and D in some stage from this. Okay, so what we do is after when we reach a successor state that we reach by applying an operator O, all landmarks that do not contain this operator O are also landmarks in the successor state, so we can just keep them. All landmarks that do contain the operator O, for those we can no longer guarantee that they are landmarks, so we discharge them. And by discharge, I mean we undo everything we did to when we first discovered them. So when we first discovered them, we reduced the cost of the operator by the cost of the landmarks, and we undo this by just returning the cost of the landmark to the individual operators in this landmark. And this change in the cost function can influence the Hmax value. And if the Hmax value increases, one can actually show that the LMCAT algorithm will discover a new landmark from these cost functions. So if we already know some landmarks, we can just start the LMCAT algorithm with this set of landmarks already computed. And let me go back to the example. So in this state, we have 4 successors. We can open each of the doors A, B, E, and F. And if we open door A, we copy all the landmarks, remove the one that contained the operator we just applied, and in this case, even if we return the cost of opening door A to the operator, we won't find a new landmark. Opening door B, you've already seen before. We copy all the landmarks, we remove the landmark that contained this operator, and since the cost of operator C and D are returned, we can discover them as part of a new landmark. A similar thing holds for door E. We copy all the landmarks, we remove the landmark that contain this operator, and we can now discover a new landmark that is F or G. And we couldn't find this landmark before because the cost of opening door F was tied up in the other landmark. And for the last successor, this is similar to the first one. If we remove the landmark that contained the operator we applied, we will not be able to discover a new landmark. So how does this work in practice? First I should say where we evaluated, how we evaluated this, and this is similar to what Martin just told you. We evaluated this in the domains where LMCAT is applicable. So these are the 44 domains. And we used the standard IPC competition settings. What I want to talk about here is the coverage, so the number of tasks that were solved, the time it needed to solve them, or the reason for failure if they weren't solved. So the first idea is just to store every landmark and use a regular A* search. A side note, Malte already said that in the workshop that the LMCAT heuristic is just a little bit inconsistent, and storing all the landmarks actually makes the heuristic consistent. So if we compare the results with a regular A* search with the regular LMCAT, we can see speed-ups by up to an order of magnitude. That means tasks are solved much faster, but they also, this comes at a cost of using much more memory. So if we look at the number of times the memory was exhausted, this increases from 31 to 526. So with LMCAT, we run out of memory very rarely, and with incremental LMCAT, almost all the reasons for failures are running out of memory. But still, overall, there's a small increase in coverage. So the main reason for failure is that the landmarks take up too much space. But this shouldn't be a problem because we can always remove some of these stored landmarks. And if we reach a node where we don't have any stored landmarks, we can just recompute the landmarks by running regular LMCAT. So one easy fix is to just remove all the information for closed nodes. As soon as we close the node, we just throw away the landmarks. Because they would only be needed if the node was reopened. And if we store every other landmarks, this won't happen. If we look at the results, these are scatter plots of the search time. So you have LM_cut at the bottom here, and the incremental LM_cut on the y-axis. And each dot represents the search time needed for each of the algorithms. So a dot in this lower part actually means that the incremental solving was faster. So overall, overall task, there's a speed up of about 77%. And in some domains, it works even better. So for example, in Myconic, there's a speed up of 93%. And you can see that in red here. And the coverage, the overall coverage increases as well. But there is still a problem of a lot of tasks running out of memory. And the question now is, why should we ever stop because of exhausting memory? Because we can always free up some memory just by removing stored landmarks. So always there is, except the 33 tasks that were running out of memory with LM_cut. So one thing that we tried was to use a fixed memory bound, just keeping track of how much memory we already used, and removing half of the stored landmarks whenever we hit this bound. An even better approach would be to make this bound dynamic instead of fixed, so just using all of the available memory for storing landmarks. But this is technically very challenging because it requires to measure the memory pressure of the program and also the memory requirements of the program accurately, which is hard because of the data structures in C++, and the overallocation they use. It's hard to predict how much memory will be needed, actually. So for this dynamic memory bound, we estimated the results as we estimated a task is solved if it was solved with any of the fixed memory bounds. So if we look at the results, we see improvements in coverage even for very small memory bounds. So even if we use only 50 megabytes for storing landmarks, there is an increase in coverage. And this increase in coverage actually increases with the memory up to some time. So there is a sweet spot for about using 500 megabytes for landmarks. And in this graph, you can see the failure reasons for different tasks. And as expected, the timeouts decrease here in black. Decrease with an increasing limit, but the memory exhaustion increases. So some tasks that were running out of time before now run out of memory. But something that is a bit harder to see because of the scale of the graph is that the total number of errors actually has a U form here with an optimum of 500 megabytes in this case. So coverage overall increases again, and with a dynamic bound we estimate that we could get an even higher coverage. Okay. So another approach to save even more memory and to still get the speed up of the incremental computation relies on the observation that there's a lot more generated nodes, more generated nodes than expanded nodes. And in the benchmarks we have, this is about a factor of 8. So only every 8th node is expanded. So if we can save a little bit of work during the node generation, this actually would allow us to amortize a lot of work during node generation, during node expansion, sorry. And this is what we did with a technique we call local incremental computation. Whenever we reach a node, we compute the landmarks for the parent node non-incrementally. Then we incrementally compute all the children. that are expanded, that are generated during the expansion. And after that, we just throw away the stored landmarks for the parent. And this is only a very minimal memory overhead because we only ever need to store the landmarks for one node at a time. So if we compare this with the non-incremental LMCAT, with non-incremental LMCAT, we have one non-incremental computation during node generation and no work during the node expansion. And with the local incremental computation, we have also one non-incremental computation, but only one for each expanded node. So this happens much less than the generation. And for the generation, we have an incremental computation, which is much faster. So overall, this pays off. We still have a lot of runtime decrease, about 50% in the geometric mean over all domains, and still about 90% in the myconic domain. But we also have some increase in the OpenStax domain, which is in blue here, just about there. And there's a 40% increase in runtime. And we have some ideas where this is coming from. So one of the things in OpenStax is that it doesn't work well with LMCAT. So the heuristic value for most states is 1, and for the goal states it's 0. And there are a lot of zero-cost operators that don't actually increase the Hmax value when we apply them. So we are basically doing a blind search here. And the overhead of checking whether the landmarks are applicable, whether we use an operator from a landmark, just takes up too much time, and we don't gain anything by it. So as a last technique, I want to talk about IDA star, because this is like the typical approach if we have memory problems with a search. We also use an IDA star search, but we changed it a bit because we actually have enough memory to store all the search nodes. We just have problems with storing the landmarks. So what we used was an infinite-size transposition table, which means that we can do perfect duplicate detection. And we can also store heuristic values for the inner nodes of the search tree, which means we don't have to recompute them. And this sounds strange at first because we have the negative impact of the huge memory requirement of A star and also the iteration of IDA star. So we have a worse thing of both algorithms. But we actually have one remaining advantage, and that is the depth-first expansion order of IDA star. And this allows us to store landmarks only for one branch in the search tree. And if we look at the results, this actually gives us the best coverage result so far. But we have to take this result with a grain of salt because these results are skewed by the good results in the OpenStax domain, which is here. And the OpenStax domain seems to benefit very well from the IDA star search, and that is not an impact of the incremental computation, that is just an impact of the different search technique. And our theory is that this is based because the IDA star search prefers nodes that are deeper in the search tree, thus just tries to apply more operators and reaches the goal earlier. And this already explains 14 of these additional tasks we can solve. But even without them, there is still some increase, and as you can see, it's still faster in most of the cases. So in conclusion, we've seen that the incremental computation of LMCAT actually makes the LMCAT computation much faster, but it uses much more memory, and there are different ways of dealing with that. What worked best, in my opinion, is the local incremental computation. We also tried using fixed bounds and IDA star. And I guess the interesting thing about the local incremental computation, for example, is that it's not limited to LMCAT. So the only necessary condition for that, to use that, is that the incremental computation is much faster than the non-incremental computation, and missing information can be computed non-incrementally. So we think that there is a lot of possible ways to apply this to other searches. So thank you for your attention.